Welcome to the Research Cortex's AACTO Abridged. Today we're going to look at the first part of a master's thesis by UT student Jonathan C. Johnson titled Summation Chains of Sequences. And the first part is going to talk about the introduction of what exactly these are, how to generate them, and some key definitions. We have all seen sequences of numbers before, lists of numbers that follow a pattern. Let's look at an example. This sequence of numbers has a pattern. We can generate the next two numbers in the sequence by adding the previous two. So look, 1 plus 1 gives me 2, 1 plus 2 gives me 3, 2 plus 3 gives me 5, and so forth. This famous sequence is called the Fibonacci sequence, and each number in the list is a term. Now we'll write these terms typically by their index, so a sub 1, the next one is a sub 2, the next one is a sub 3, a sub 4, and so forth. And then we'll denote a as the sequence of these numbers. Let's look at a few more examples. Here's another sequence, and this one's pretty simple. It's simply formed by alternating ones and zeros. So the odd terms are a 1, the even terms are a 0. Let's take a look at this one. 1, 4, 9, 16. Now this one is generated by the sequence of perfect squares. So 1 squared is 1, so 2 squared is 4, 3 squared is 9, 4 squared is 16, and so forth. Then we can look at this one as another example. This is 1. Then 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 5, and so forth. So any generic term is simply 1 divided by n, where n is the index just like we see here. The last one we'll just take a look at, just so that you know that not all sequences have to start with 1, is this one. So we'll start with 8, and then 0, and minus 8, minus 16. The pattern here is pretty clear. We subtract 8 from the previous term to get to the next term. So 8 minus 0, 8 minus 8 is 0, 0 minus 8 is minus 8, and so forth. People have been fascinated with sequences of numbers for a long time. There are quite a few things about a sequence that we can explore to look for interesting patterns. One such object that we can build from any sequence is the sequence of partial sums. This is a sequence that keeps track of the running total of the terms in our original sequence. Let me show you what I mean by doing this on our Fibonacci sequence. So if we want to build the sequence of partial sums here, well, 1 just stays. Now the next one we're going to do, the second term of the sequence of partial sums, is the first term of the original sequence, 1, added to the second term of the original sequence, 1. So it gives me 2. Then the next one, it's still the running total, right? So we want to add 1 plus 1 plus 2 up to 3. And that gives me 1 plus 1 plus 2 is 4. And now you can start to see that an easy way to generate a sequence of partial sums is to add the next term to the sum of the previous terms. So 4 plus 3 gives me 7. 7 plus 5 gives me 12, and so forth. And then this way we can generate the sequence of partial sums for the Fibonacci sequence. Let's do one more example. Let's look at this sequence of alternating ones and zeros. So again, the first term in the sequence of partial sums is 1, and then the next one is 1 plus 0, well that's just 1. Then the third term in the sequence of partial sums is 1 plus 0 plus 1. That gives me 2. Now, the fourth term, 2 plus 0 equals 0. And you can start to see the pattern here. In general, to take a current sequence A, given by A1, A2, A3, and so forth, the sequence of partial sums, and we'll denote that A sub S, can be given by A1, then the next term, A1 plus A2, just like we've already done, A1 plus A2 plus A3, and in general, the nth term of the sequence of partial sums is the sum from 1 to n of the previous terms. Using that generic formula, we have then also calculated the sequence of partial sums for each of the other example sequences here. Something else we might be interested in, given a sequence of numbers, is called the sequence of differences. This is created by looking at the difference between any two successive terms. Let's see an explicit example on the Fibonacci sequence here. So let's just leave the first term alone, and then the difference between the second term and the first term is 1 minus 1 is 0, and then 2 minus 1 is 1, 3 minus 2 is 1, 5 minus 3 is 2, 8 minus 5 is 3, and you're starting to get the idea here. Interestingly enough, notice that the sequence of differences of the Fibonacci sequence is actually the Fibonacci sequence again with a 1 and a 0 at the start. Let's do another example with the sequence of alternating 1s and 0s. So its sequence of differences, the first term is just the first term. The second term is going to be the second term minus the first term, which is a minus 1. And then the third term minus the second term, so 1 minus 0 is 1. Then 0 minus 1 is a minus 1. And I think we get the idea here. For your convenience, I have calculated the sequence of differences for the other sequences in our example. A couple interesting things to note here. This one, remember, this one was generated by perfect squares, so 1 squared, 2 squared, 3 squared. If you look at the differences between any two perfect squares, notice that they actually follow a pattern of odd numbers. And the last one here, this one is pretty standard. How did we generate this one? Well, we simply subtracted 8 from the previous term, so it makes sense that the sequence of differences minus that first term is essentially the same, just a constant minus 8. Now, if we write this out in general, given a sequence, A equals A1, A2, A3, A4, so forth to AN minus 1, AN, and we don't assume that it's finite, so let it keep going. Then its sequence of differences, I'm going to denote that A sub D is given by A1, then A2 minus A1, A3 minus A2, right, the difference between two successive terms, A4 minus A3, and in general, the nth term is AN minus 1. Here's the Fibonacci sequence again in white. We have already calculated the sequence of partial sums above in green, and the sequence of differences below in purple. Each of these is also a new sequence, and we may look at either the green or the purple sequence, and then calculate their sequences of partial sums and sequence of differences. Let's actually look at calculating the sequence of differences of the sequence of partial sums of the Fibonacci sequence. So remember, the sequence of partial sums, so A sub s, is this little guy in green. We're going to put A sub 0 here, and then the sequence of differences is right here. Now let's calculate the sequence of differences of A sub s, the sequence of partial sums. Well, the first one is just 1, and then what do we get? The next one is going to be, so the first term of the sequence of differences of the sequence of partial sums is just 1, and then 2 minus 1 is 1, 4 minus 2 is 2, 7 minus 4 is 3, and gee, this is starting to look awfully familiar. 12 minus 7 is 5. So the sequence of differences of the sequence of partial sums brings us back to the original sequence. So let's do it the other way. Let's look at the sequence of differences in purple, and let's look at its sequence of partial sums. The first term is just a 1. Then we have 1 plus 0 is 1. 1 plus 0 plus 1, or 1 plus 1, gives me, so 1 plus 0 plus 1 gives me 2. 1 plus 0 plus 1 plus 1 gives me 3. So adding all of these up. Then 3 plus 2 gives me 5. And you can see here what the pattern is. The sequence of partial sums of the sequence of differences gives me back my original sequence. So what do we actually have here? We have this concept of partial sums, and then we have the idea of differencing a sequence. These things can be termed operations. So these are operations that we can do to a sequence. And since the sequence of partial sums, by differencing that we get the original sequence back, and by giving the partial sums of a sequence of differences we get the original sequence back, these are considered inverse operations of each other. Now we notice that with these operations we can start making chains of sequences. We go up the chain, so up the chain, by creating the sequence of partial sums of the previous sequence in the chain. So notice the green one is the sequence of partial sums of the previous one, and this above white one is actually the sequence of partial sums of the green one. So it's the sequence of partial sums of the sequence of partial sums of the Fibonacci sequence. We go down the chain by creating the sequence of differences. So from this white one, which is our original Fibonacci sequence, so let's call him A sub 0, we move down by creating the sequence of differences, and we move down one more time by taking the sequence of differences of that sequence of differences. So the notation used in the paper to denote where we are in the chain is given by A, and this is not actually an exponent, this is just an index. So A0 is the original sequence we started with, and if we go up 1, then we've taken partial sums. When we go up 2, that's the partial sums of partial sums. That means we're 2 levels up the chain from our original Fibonacci sequence. Likewise, when we go down, that's a -1, we take a sequence of differences. So from 0 to the purple one, that's a sequence of differences of the original sequence. And then A -2, so this index, tells me we're 2 levels down, and it's obtained by taking the sequence of differences of the sequence of differences of the original chain. So if we want to get from A2 back to A1, we need to difference the sequence. If we want to get from A -1 to A0, we take the sequence of partial sums. Let's change gears and focus on the sequence of alternating ones and zeros. That way our arithmetic will get a little bit easier. So this one is highlighted in white. We've seen this sequence before. Now I'm going to organize this chain of sequences a bit differently. All I've done with its chain is remove the parentheses and stacked them. So let's let the index M look at the row, right? And let's let N look at the column. So M gives us the number sequence that we're on. So right, this one is the original one, ones and zeros, so that's 0. Then the sequence of partial sums of that is a 1. Sequence of partial sums of that one is 2, 3. And the sequence of differences, right, -1, -2, -3. Remember, our indices can be negative here. Now N, the indices are always positive, right? These are terms in the sequence. 1, term 2, term 3, term 4, and so forth. Let's call this whole chain, or this matrix, C. Now C, M, comma, N is going to give the position of a particular number in this chain. So let's do an example. Let's find out where C2, 4 is. Well, C2, 4, we need to go up to sequence number 2, 1, 2, and then the 4th position in that sequence, so 1, 2, 3, 4, and that is equal to 5. Let's try one more example. Let's do C -1, 8. So how do we find that one? Well, we need to move to -1, so this sequence here, this row, and the 8th position in row -1. So 1, 2, 3, 4, 5, 6, 7, 8. C -1, 8 is equal to -1. So question, how do we calculate an entry in any part of the chain? Since we move up the chain by partial sums, then we have that, let's do this in white, CMN is equal to the sum from K goes from 1 to N of the previous sequence, so that's m minus 1, and add up the entries in the previous sequence from 1 to n. So let's do a quick example. Let's look at calculating this one. So remember, what is this? This is index 0, this is index 1, this is index 2, 3, minus 1, minus 2, minus 3. So the number 2, so 2 is equal to C1, 4, and we can get that by this formula. So it's going to be the sum from k going from 1 to n is 4 of C, now m was 1, so C 0, k. That means we're going to be looking at the terms right here to get those numbers. So that's, let's do this in white, it's going to be C01, which is 1, plus C02, which is 0, plus C03, which is 1, plus C04, which is 0. That's indeed 2. Now, if I wanted to compute, for instance, C10, 2, so the second entry in row 10, and I only had the original sequence, say this guy, which is index 0, I would have to do quite a bit of annoying arithmetic to get all the way up to that part of the chain using the formula we just looked at. Jonathan Johnson in this paper has proposed a quick way to calculate any entry, or any entire sequence for that matter, in any row. So let's denote M1 and M2 to be generic indices. Remember, those are the rows, right? So M goes up this way, and N goes along and counts the columns. So M1 and M2 are rows, or actual sequences. And we're also going to put the condition on here that I want M1 to be greater than M2. And we're also going to take any old n that we want. So any n, now n that's an index, right? 0 or 1 through whatever. And I'm also going to define one more quantity. Let's call just regular old m, let's take that to be the difference between m1 and m2. So this is m1 minus m2. So what are we actually going to do? Supposing that I already have a sequence with row index m2, we want to be able to calculate any term in the sequence with index m1. And that formula is given in Jonathan Johnson's paper and is right here. So the sequence of m1, any one in there, and so any n, can be calculated from the sequence m2, which we already have, in this following way. So we simply have to add from the terms 1 through n. It's going to be the terms of row m2, so the first through nth term, and we're going to multiply that by this quantity. Now remember, this is called a combination, so real quick, so I'll use different indices. A choose B is equal to A factorial divided by B factorial times A minus B factorial. Let's actually try this out. Suppose that M1 is equal to 3 and M2 is equal to 0. Let's also pick a particular n. Let's just say n is going to equal 3 as well. So we want to find the third term of the third sequence in the chain that is built from alternating 1s and 0s. So remember, this guy is 0, 1, 2, 3. Now I've left the chain that we've already calculated by hand down there. That way we can kind of verify our answer. But we're still going to use this formula and calculate it that way. So in this case, we also need that m is equal to m1 minus m2, which is 3 minus 0 is equal to 3. So C3 and n is 4. I'm sorry, n is 3. Let me erase that. So C3, 3 is going to equal the sum, k goes from 1 to 3, of what? Well, we have m is 3 plus n is 3 minus k minus 1. Choose m minus 1, which is 2. 3 minus 1 is 2, times C0k. So we're going to be looking at the 0 row here. So the 0 row. Alright, here we go. So this is going to equal 3 plus 3 is 6, minus 1 is 5, so it's going to be 5 minus, now the first one, k is 1, choose 2. Now C01 is, so C01 is down here, that's 1, plus 5 minus k is now 2, right? We're adding the next term. Choose 2. Now C02 is 0, but that's okay. Plus 5 minus 3, choose 2. C3, 3. C03 is 1. Alright, so that is going to be, let's move this down here for now. So this is equal to 5 minus 1 is 4, choose 2, times 1, plus, that's just 0, plus 5 minus 3 is 2, choose 2. So 4 choose 2 is 4 factorial over 2 factorial times 2 factorial. And then we have 2 factorial over 2 factorial times 0 factorial. So this is going to be 4 times 3 divided by 2 factorial plus 1. And that's going to be 6 plus 1 equals 7. This paper formalizes the notion of a summation chain of sequences, and in addition to the neat formula we just discussed, gives some other consequences of that formula. Thanks for watching AACTO Abridged at the Research Cortex. We'll look at Part 2 next time.